So can everybody see my screen?
Perfect.
Great, okay. Hi everyone, my name is Omar. Today I will be discussing recent project on particle injection and non-thermal particle acceleration in relativistic and magnetic reconnection. And so this talk will be split into two parts. Why doesn't it let me do this? Oh, I see. Huh. Oh, there we go. Okay. So we'll be organizing this talk into two parts. And the first part will be on particle injection. And the second will be on non-thermal particle acceleration. Before I define these terms, however, we will briefly have an overview on what relativistic magnetic reconnection is, including some of the astrophysical systems in which it's present and some of the fascinating theoretical challenges it poses for us. And throughout this talk, I should clarify now that quantities highlighted in green will have relevance to particle injection, and quantities highlighted in red will be more relevant to high energy acceleration. So to begin, magnetic reconnection is a plasma process which rearranges magnetic topology and rapidly liberates magnetic energy into heat, bulk flows, and non-thermal particle acceleration. And it is this third channel which we are interested in studying in this project. What we mean specifically by relativistic reconnection is when the plasma is magnetically dominated such that the magnetic energy density of the reconnecting magnetic field greatly exceeds that of the rest of plasma. And so I've shown a figure here, sort of a cartoon of magnetic reconnection. And in this figure, we have B0, which is the reconnecting magnetic field shown in blue. And within this diffusion region, particles are flowing in, and within the diffusion region, they are accelerated out of plane by an electric field induced by Faraday's law from the reconnecting topology, magnetic field. However, after this reconfiguration, magnetic field lines that are reconnected flow downstream, shown by these red arrows here, and with those field lines are dragged those out-of-plane accelerated particles, which creates the outflow. It is for this reason that reconnection is typically described as a two-dimensional process, and therefore, for many years, has been simulated in only 2 dimensions, although there are some 3-dimensional effects which are important to consider, although we will not be doing that in this project. You'll notice within this diffusion region, there are these substructures, which are called plasmoids. And if you look carefully, you will see that between each of these structures, there resembles a magnetic field structure similar to B0 on the broader scale. And these structures in this plasmoid-dominated regime of reconnection propagate a self-similar hierarchy down to smaller scales. And for that reason, reconnection is understood to be a multi-scale process, and it is poses some interesting challenges from this. So to discuss some of the astrophysical scenarios in which relativistic reconnection may take place, we'll begin with AGN jets. And here's a movie by Bart Rippeda, and it shows accretion. I think this is a simulation, and so it just shows accretion around a black hole where it's expected that reconnection should happen close to the black hole, although it's not something that has been observed, and there's still a lot of work to be done in trying to connect the particle acceleration processes to the radiation signatures. And another such system is a pulsar wind nebula. So here's an observation, 2 observations of the Crab Nebula pulsar wind. One is from Chandra, which is in X-rays, and the other is from Hubble. So this movie is from NASA almost 2 decades ago. So in these systems, we have a relativistic plasma, and that's relevant for relativistic reconnection. However, there scenarios where non-relativistic reconnection may be relevant are ubiquitous to the universe, maybe much closer to home, such as in the solar corona and the Earth's magnetotail and many other astrophysical systems. Relativistic magnetic reconnection may also be a source of gamma ray flares, which is an exciting frontier in trying to understand the origin of those. It's still one of the great mysteries in astrophysics. So just to finish discussing astrophysical applications, here's a figure from a paper a couple of years ago by Bart Ripida, Fabio Bocchini, and Sasha Filipov. And it shows that near a black hole, you may have these contours. This color bar here is showing the plasma beta, essentially. And so closer to the black hole, you will have low beta, and further away, you have high beta. And that indicates that you might have fast reconnection near the black hole, and further downstream, you might have more plasmoids. And that is what we see as you proceed through this movie. So this is just sort of to capture your interest, if this is something that interests you with astrophysical applications.
Got a question.
Yeah.
So in this case, like, where's the current sheet and where are the opposing magnetic fields for the reconnection?
A bit hard to see, but it's all within this, I believe it's all here.
It's probably best seen on the last image.
Sure. Last image here. There's opposing, it's, as you can see next to the black hole, there's an opposing field structure that turns as you proceed down in RK sine theta.
Okay.
Yeah. So question is, how do we investigate particle injection, non-thermal particle acceleration? And what we decided to do is to run simulations, and we have pretty simple reasons for doing this. The reconnection and particle dynamics are too complicated for an analytical treatment, which is more conventionally used in a collisional, maybe not plasmoid dominated regime, maybe resistive MHD. But in this case, when you have fully collisionless plasma with we need a fully kinetic description, and therefore we run simulations to obtain that information, and therefore we run these particle and cell simulations. And this enables us to find particle trajectories and particle energy momenta, as well as the fields that are encountered by particles, namely electric and magnetic fields. And so this information, as we'll see soon, is instrumental for a complete description for just the particle energization from reconnection. And that is what we'll discuss next. So our simulation setup, we use a code called VPIC, which solves the relativistic Maxwell equations. The simulations are in 2D and use a pair plasma. And so here I have a movie showing how the current density evolves with time, which is quite revealing. It shows distinct regions, one moving region where there's a lot of dynamics, the other stagnant. So the stagnant region will be more the upstream region, as we'll see later, and the evolving region is what we call downstream. In this simulations, we have an initial temperature, which is non-relativistic. However, the magnetization indicates that it's a magnetically dominated plasma, meaning that the downstream region will have a fair number of relativistic particles, which creates this distinction. This upstream is non-relativistic and the downstream varies, but has a lot of relativistic particles. So those what we discussed were fixed parameters in our simulation. We have two scans in our simulation. One is over guide field strength, which is the ratio of the guide magnetic field to the reconnecting magnetic field. The other is system domain size, which is the ratio of the system length over the magnetization. What we're normalizing by the magnetization times the nominal relativistic gyro radius. And the reason for normalizing by this factor is that it allows us to contextualize our domain size in terms of the upstream magnetization, which can be useful for systems in which the the scaling depends on the upstream magnetization. So it's sort of a contextualizing normalization factor. And to those who are familiar with simulations of the sort, the initial current sheet is force-free, the boundaries are reflective in Z and periodic in X, and the simulation running time of each simulation scales according to this domain size Lx, so that the ratio of the box length over the total running time is constant. And so just to show, for example, in this movie, what the dimensions are, the snapshot being shown here is about a third in either dimension Z and X for the domain. So maybe wondering why bother scanning on these parameters? So the guide field strength actually has a very considerable influence on the reconnection physics, as well as the particle acceleration evolution. And it is also a parameter that varies widely throughout the universe. And so it's of course one of the most important parameters to vary in a study like this. What about system size? With system size, this was of primary interest because if a parameter converges with increasing system size, and then it may indicate that this parameter will no longer grow with system size, and this may be propagated to astrophysical scales, which are impossibly large to simulate. And so if you're interested, the initial magnetic field is as follows, with the half thickness of the initial current sheet being about 6 skin depths or 1 sigma bone. And in this equation, we can see that if you increase the guide field strength, Bg, the amount that the magnetic field rotates as one crosses over the z=0 plane will decrease. With a guide field of 0, it's 180-degree rotation. With a guide field of 1, it's a 90-degree rotation, and it proceeds like this. Okay, so the first part of the talk will be on particle injection. And over the past decade, we have made a lot of progress on this in this field. This is sort of began almost 10 years ago. And the real question here is, we know that PIC simulations produce power law spectra. However, the question is, how are particles promoted from a Maxwellian distribution to a power law distribution? And so as you can see in this figure, at time t=0, we have a Maxwellian distribution, and somehow as time proceeds, a power law is over. And really the question is, how are these low energy particles brought to these higher energies? So our methodology is to define the injection energy precisely, and that involves creating some kind of fitting procedure to determine this quantity gamma injection, and therefore, this gamma injection value defines the low energy cutoff of the power law distribution. And what we find is that by this definition, particle injection simply means acceleration up until gamma injection. And we have a fitting routine to calculate gamma injection, which we'll not discuss in this talk, but you can find in my paper, which will be submitted soon, hopefully. Okay, so also if anybody has any questions throughout, please feel free to interrupt. That's also okay. So now we'll begin to discuss injection mechanisms, which we consider 3. The first we consider is direct acceleration, in which, and in fact, for all of these injection mechanisms, the incident particles are from the upstream. This is sort of this distinguishing feature of injection. So for direct acceleration, the particle comes from the upstream and directly enters the reconnection electric field, the fusion region, and as shown in orange here, there's this out-of-plane electric field which accelerates the particle. And as discussed in the beginning, the particle is sort of dragged by the freshly reconnected magnetic flux and is still attached to field lines as it begins to flow downstream. And whenever the guide field is greater than zero, the reconnecting electric field approximates the parallel electric field when guide field is simply out of plane. Second, we have Fermi kick, in which a particle is flowing in from the upstream, and in the same way that a tennis ball will encounter a moving tennis racket and be accelerated, it will encounter this reconnection outflow and gain acceleration due to a induced out-of-plane curvature drift that is aligned with the local electric field. Shown here, there's an electric field pointing into the page, and there's also V-curve curvature drift aligned with it, and that creates a kick in the from electric fields perpendicular to the local magnetic field, which is now in plane. Third, we're considering is pickup process, in which particle directly enters the downstream from the separatrix, crossing over a separatrix, and this process is different in the sense that the magnetic moment, which is typically an adiabatic invariant, if the magnetic field is sufficiently slowly varying, is no longer invariant. The invariance of the magnetic moment is violated, and the particle gains significant perpendicular momentum. And this process is also caused by perpendicular electric fields, as we will see in a second. So what we notice from looking at these three injection mechanisms is that the arrangements of the electric and magnetic fields are the same. So magnetic field structure looks the same, electric field looks the same, but the regions of acceleration are different. So with the direct acceleration, we accelerate in this diffusion region. With Fermi kick, we're sort of somewhere here, and with pickup acceleration, we're further downstream. And so it might seem a natural way to study this process is to look at the location of injection. However, each particle also has a unique experience of which electric fields accelerated and which components of momentum are gained with respect to the local magnetic field. And so therefore we have this different way of categorization, which doesn't require us to identify these structures with some rigorous procedure. All we have to do is calculate the work done to the particle by different components of the electric field, and also the different momentum components gained by the particle with respect to local magnetic field. And so you'll see these expressions up here, such as W parallel greater than W perp and P parallel P perp. What this means is this is the work done by parallel electric fields as a function of time, and this is for perpendicular electric fields, and these momenta components are calculated in the E cross B drift frame. And that is done because we're interested in relative to the bulk plasma motion, what these momenta component gains are. Okay. So to be specific, upon reaching gamma equals gamma injection, a particle is categorized according to whichever of the following conditions happens to be true at that instantaneous moment. Now, while we should recognize that multiple injection mechanisms can work together towards injecting a particle. However, we are intending to, we in fact perform all of these, we check all of these conditions over an ensemble of particles, hundreds of thousands of particles, which gains us a statistical measure. And so despite this sort of maybe misleading categorization, using a large statistical ensemble, we can gain a reasonably accurate statistical measure of each mechanism's contribution to injection.
Could I ask a quick question?
Yes.
So is gamma injection just a parameter that you choose to be kind of close to the tail of the initial particle energy, or?
We have a fitting procedure for rigorously calculating it. It's different for every simulation. If you're interested, it's in the appendix of paper we're about to submit, but I won't go into the fitting procedure now, unless, I mean, maybe we can talk about it after.
Maybe you can just describe it. quickly
Yeah, like
for
a
the-
good
Sure. So essentially,
What's the minimum coverage?
right, so if you have a if you perform a fitting procedure to determine the power law index, you know how far it proceeds up and back, and what the ratio of the gamma to the minus p distribution is versus f. So you have this how far does the spectrum deviate from the power law fit?
Maybe you could
And-
flip back to the picture of the spectrum.
Sure.
Spectrum.
Right, so if we're at this point here, this power law distribution extends in both directions. It's just a straight line. And if we have a procedure for determining when does this straight line deviate from the spectrum by a certain amount, then we can say that's gamma injection. In the same way that you would determine the cutoff by proceeding down this slope and seeing when does the spectrum deviate from the power law fit by some amount that is chosen appropriately.
And
I
it's
see.
just, at what time?
Final
Like,
times.
so you're looking at the final time and then it applies retroactively to the entire simulation?
Yes. So that is one aspect of it. So at the final times, we determine the injection energy because that's when the power law is most stable. That's in fact, if we try to calculate it as a function of time, probably would be run into some problems. But that would certainly, if it could be done, that would be that'd be good if it could be done. But yeah, we calculated final time and retroactively apply it.
And then if you have two different simulations, is it basically the same in both simulations or?
Yes, so if we'll see later, later on I will show values of gamma injection over all the guide fields and all the domain sizes, and there's pretty clear trends. So for the same, if you have the same guide field and change the domain size just a little bit, you get pretty much the same gamma injection. But if you change the guide field, actually the injection energy changes. So that's another interesting feature. It actually has quite important implications for the injection.
So, but basically, just to mention, so overall, the non-thermal part of the distribution function is characterized by the three parameters: the power law slope, the high energy cutoff, and these have been investigated a lot in the past, including by Greg. But then also there is the low energy cutoff of the power law, which is what Omar calls injection energy. And these three parameters are functions of the simulation parameters. The simulation parameters investigated in the study, as Omar explained, are guide field and system size.
Correct.
So there will be some information about these
Yes.
dependencies.
I mean, technically, it should be 4 cameras, right? You can get normalization.
There is normalization also. right?
That's right. But dividing by the
But is
norms,
that just determined by fund?
I mean, yeah, I mean, this vertical axis can be normalized by the integral of the entire distribution. So, any other questions on this one? Okay, we can proceed. Right, so we run through these conditions for an ensemble of particles, which gains us a statistical measure for each mechanism's contribution to injection. And so, as an example, yes. Mhm.
Feedback, yes. Could you comment on the difference between the Fermi kick and pickup acceleration conditions in terms of p parallel or p perpendicular? Why
Yes.
it's chosen?
Yes, so for
Parallel and perpendicular.
right, so for Fermi kick, despite the fact that a perpendicular electric field accelerates it, so the electric field's in plane and the magnetic field, electric field's out of plane and magnetic field's in plane, the particle stays attached to a field line, and therefore most of the momentum is gained in that parallel to B, whereas for a pickup acceleration, of course there's still magnetic fields around, but the local magnetic field, the particle's magnetic moment loses its invariance, and because it very rapidly goes from being in a non-relativistic plasma to a relativistic plasma. It enters this region very suddenly, and its magnetic field changes very quickly on a short time scale, which gives this perpendicular moment.
And how are energy and momentum different? Is P prime in a different frame?
Yes, prime in the cross B drift frame.
So, and there's a final momentum or initial momentum when they, I mean, for a particle, is it, you don't have delta P, you have P itself. So
Yes.
is this the momentum after the, at the injection time?
Yes, so this is, so these momenta are functions of time. There's just the momentum of the particle.
Right.
And
When you apply this condition,
yeah, so this condition is applied at T injection, let's
Okay.
say call it T injection, which is the instantaneous moment when the particle reaches gamma injection.
but basically this condition, whether, you know, comparing parallel and perpendicular momentum can be recast as just a pitch angle. Like,
Yeah, could be.
in that frame.
Yeah,
Sorry, you said what? Recast is what?
As a pitch angle.
yeah, it could
Parallel comparing whether it's more parallel or perpendicular.
could be.
And for that matter, both of them are pitch angles in two different frames.
Mhm.
But the
Well, it's in the same
energy-
frame, right?
Well, yeah,
But
but
the prime frame is the same.
Oh, I mean, the energy criterion and the momentum.
Right, but I'm
criterion.
just talking about the momentum criterion. Yes, the energy worked out, yes, it's a separate thing,
Mhm.
but it's the same, I mean, for the last two lines here. The work done criterion is the same, so you first apply that and then you can decide,
yes,
essentially based on the pitch angle.
yeah. So you can recast it as pitch angle, and in fact, you could create a phase diagram of like essentially pitch angle versus like I don't know what you want to call it, like electric field angle between magnetic field, and you could probably make a very nice figure with that, but we covered that. Okay, so for an example of this, let us consider. Hopefully, I guess this movie isn't playing. I don't know why it's not playing. Okay, well,
If you stop sharing your screen and just for a few minutes. If you stop sharing it and just try to play it
yes,
outside of,
okay,
if you go to.
Maybe the laser pointer affects.
I
Yeah,
see.
now the people on Zoom can't see it, but.
Yes,
Exclusive content. Yeah.
No, sorry, but are you logged in? If you stop sharing it. And
there we go. Yeah, I don't know what's going on. Well, if we,
I think if you turn off your laser pointer feature, it will be able to click.
oh, now it works. Okay. So let me. Okay.
If you could just turn your laptop to face the screen.
Okay, can everybody see this?
Oh, yeah, it's working now.
Okay, so can everybody see this movie? Okay,
Yeah.
so this is an example of a particle trajectory. And so what you see in orange here is particle, and it was experiencing pickup acceleration. So I'm showing the work done to it, and we can see that the perpendicular component has this big gain, but the parallel component remains essentially close to zero. And I don't show it, but the perpendicular momentum also is increased. So imagine,
could you run again?
well, yeah, sure. So if you could imagine performing this over many particles and
Oh, sorry, so you should.
countertops.
So when does it, could you explain? I mean, explain the movie, explain what happens. What is the moment of time when the pickup happens?
Sure.
That we understand.
So if we have,
And maybe stop at that moment.
yes, so if we have a particle,
So it crosses
Upstream.
the separatrix,
so
right?
at the current moment's in the upstream, and there's now flow approaching it. And at this moment, it is on the exhaust boundary, more or less, right? And this, you can see this red dashed line is instantaneous moment in time, and the work done to it by perpendicular electric fields proceeds to increase, and
So just
it
sharp
increase-
right here.
yes,
It's not
and
better processing.
right, and in fact, for this simulation, the injection energy may be somewhere around 8 or so. So this particle we would consider to be injected by this mechanism,
By which mechanism?
pickup acceleration. Since this is sort of a pickup process, it enters just crosses the separatrix. Just out here.
Because it never went through the diffusion region through the X point.
Right,
It just
yeah.
crossed the separatrix somewhere and got picked up by the outflow.
Yes,
At the same time, it also did not go through to the other side, and it didn't cross the midpoint of the reconnection.
yeah,
So just remained with the outflow.
correct.
And wait, you said the injection energy is like 8, right? But it's not there yet.
Yeah,
Yeah, it's,
So is it the
but
next part that's the acceleration part, or is it the part that just went through?
yeah, so this is the injection, what you just saw, is this is the injection, energization.
Okay, so like the injection refers to getting up to the.
Yes. And after reaching the injection energy, any subsequent acceleration, we would say is sort of post-injection acceleration or high energy acceleration or something like that. Okay, so any questions about this? So imagine,
let's watch it from the end.
sure. So this is,
So now it's gain more energy, right?
yep, and okay, as you can see, W parallel remains near 0.
Yeah, where is that?
You can't even see, that's how small it is. Yeah, so, yes,
It's
Because in this region is very far from the X point. There is almost no parallel electric field.
correct.
It's essentially a HD region.
Mhm.
And at the point of injection, there's a very large range in energy. Is that
Oh, yes, you mean this,
cyclotron motion, or
Mm.
is the span happening over one oscillation, or is it happening over many
yeah,
years?
so,
Maybe you're talking about the width of the orange.
Yeah, the height to the.
all right, so, yes, so this is I can pretend to explain it, but this happens for a lot of particles because of just probably there's a lot going on in the local frame. Okay, so
Great.
can we move on?
Sorry, what is the orange shaded region on the right again? I'm a little lost in that.
Yes, so this is which is the integral of the particle velocity dotted with the electric field perpendicular to the local magnetic field. And so this is just basically a cumulative, a quantity which represents the cumulative work, the work done to the particle by perpendicular electric fields, defined as a time integral.
If it's a cumulative quantity, okay, yeah, what can be negative, so it can also decrease, I guess. But why isn't it like a simple line? Why is it like the shaded region?
Sorry, could you repeat that?
Why is it not a simple line? Or is it like going up and down?
Yeah, it's rapidly, very rapidly oscillating here, probably on the
Okay.
order of like gyro frequencies, as Greg mentioned. I think that's probably the explanation. I mean, as we can see here, this time scale may be 100 omega PE, right? And so it's entirely possible that from one omega PE to the other, it just goes up and down and has this steady increase. That's what we're just describing.
Thank you.
Yep, thanks. Okay, so when we perform this for many particles, what we find is the following. What we find is that parallel electric fields inject the first few particles. So this mechanism is just first to inject particles, but if you wait longer, you find that the other two mechanisms which I am temporarily combining into one category, as you can see in the plot, Fermi plus pickup in dashed lines, they improve as the time proceeds. Later, we will compare Fermi and pickup, but for now, we're comparing W parallel injection mechanisms to W perp.
You should describe the plot. You should say
Yes.
what's plotted here.
So what we're showing here is the injection share, which is the number of particles, the percentage of, so we take all of the injected particles and we consider what percentage of those were injected by direct acceleration, W parallel, parallel electric field acceleration injection. And what we see is that starts out high and declines. Whereas
We lost your cursor. I just said we lost your Omar's cursor for a moment because he was explaining, but we did not see the cursor.
okay, so what we begin with is this W parallel injection, which starts out high. However, as time proceeds, the other two injection mechanisms begin to dominate overall injection. For this case, we'll see different cases, reaches 60%. Right, so this is just for comparing for a single guide field, these parameters. However, if we change the guide field.
And so is this cumulative over time, or are we looking at the fraction at a moment? of
This is
time?
instantaneous injection share. So for example, at 2000, this is at that time, what percentage of particles are injected by W parallel versus the other two combined. Right. So when we vary the guide field, we find something interesting. What we find is that the time at which W parallel becomes subdominant is delayed. Right. And so for weak guide fields, it really is a very short period of time in which we have this dominant phase of parallel electric fields injecting particles. And furthermore, as you get to stronger guide fields, the amount of dominance that Fermi and pickup have near the end weakens. So that's what we see here. And however, if you increase the guide field enough, let's say to 1.0, then parallel electric fields dominate throughout the entire simulation. And there is no point at which Fermi and pickup injection shears end up dominating. So this is an interesting fact.
Just for someone who's not super familiar with magnetic reconnection things, how much of this initial time is just transient stuff happening, like the plasma is having formed yet?
Yeah, that's going to be this initial time when there's no injection yet.
Where you're just not flying anything.
Yeah. So
That's really-
yeah. So in fact, maybe it seems weird that these lines start off not at zero. It's because at early times, so few particles are injected, they fluctuate rapidly, just the instantaneous share. So I just remove those so you can see clearly where things start up.
Actually, do you have an energy plot? I'm curious. I mean, over reconnection, at first there'll be very few particles accelerated.
Mhm.
So it doesn't matter so much what the fraction is, and at late times there will be very few particles accelerated. So it also doesn't matter. Like at what time here is the bulk of reconnection occurring?
The bulk of
injection.
If you look at the magnetic energy versus time,
I see
there'll be
it.
time when most of it is dropping.
yes. So the way I think of this, you'll have the primary current sheet, right? So this is early times, maybe before 1,000 like a PET, maybe below 2,000-ish. Where you have most of the primary, initial arrangement. That's when most of that reconnection occurs. However, later on, you may have plasmoid mergers of secondary X points can contribute later on to direct acceleration. Sure.
So I just want to clarify that here at the very end at 5,000, this is still active reconnection stage, because these simulations differ from your simulations, correct? Where in your simulations we had simulation itself lasting much longer than the reconnection time. So at the end of the day, the system settles. that corresponded to several light crossing times, right? These simulations typically end at 2 light crossing times.
Okay, so still very active reconnection at the end.
Correct. Yes, maybe I should have indicated earlier that we limit our simulations to two light crossing times. Okay. So now when we divide the previously combined category Fermi plus pickup into Fermi versus pickup, we find something quite interesting, which is that pickup is drastically suppressed over this slight variation from a weak guide field of 0.1 to a slightly less weak guide field of 0.3. Pickup acceleration is nearly cut in third, whereas Fermi is not very not
Could you
affected.
show it on the slide?
Yes, so this dotted line is the pickup injection share,
Okay.
and this as well. And so when we vary the guide field from 0.1 to 0.3, we have this huge drop, whereas Fermi actually remarkably similar for these two guide fields. And this is something that maybe I can discuss later. Is an interesting trend. So
the perpendicular injection is going down as guide field is increased. But it's only the pickup mechanism that's going down, not the Fermi mechanism.
correct for this under this variation. However, when we increase the guide field even further, we see that both are suppressed. And Fermi, in order to suppress Fermi, you need stronger guide fields like 0.5 or 1.0.
So the first, yes, it's very interesting actually. So the first drop in pickup that Omar described happens really not when you go from weak guide field to strong guide field, but when you go from weak guide field to just slightly weak guide field.
Right, exactly. So that's something that
A different scale of guide fields. Yeah.
exactly. So that's interesting on its own. Okay. And so now let us consider varying the domain size, see what influence this might have. So if we start off with a very small domain, what we see is that W parallel is completely dominant. In this case, for guide field of a half is 80%. But if you increase the domain size, or continue increasing it, we find is that the saturation of sort of as it sort of stables out of W parallel injection versus Fermi plus pickup is delayed, and also Fermi pickup shares improve. All the way to, for the largest domain we test, Fermi and pickup are actually dominant. It's just barely dominant at the end. So this trend does not continue indefinitely. So if you use, say, an infinitely large, I don't know how you would do this, but a very large box, it wouldn't have, you wouldn't see Fermi and pickup injection shares at 100%. We'll see in the next slide that this improvement does saturate and reaches a sort of a maximum level.
Wait, why is the box size affecting things?
Um,
Like, does it affect how reconnection proceeds or something?
It's just you have, I mean, there's different possibilities. So one is there's more time. So if the number of light crossing times is preserved, then a larger box means there's just more gyro frequencies that can happen, and that may improve. It's just there's more opportunities for Fermi pickup injection. Whereas I think for direct acceleration, because it's a sort of reliant on a transient thing, like maybe the initial reconnection sheet, like current sheet, that's where most of that happens. For larger domains, that sort of becomes diminished. And so.
So for instance, like if you look just at, take a vertical slice here, so at the same omega PV over two, but they're still different. Right, so, but if you were, are you saying that if you put this in terms of like light crossing times, then that would overlap?
Yes, I think the saturations would overlap, like whenever these lines stabilize, sort of. However, the values themselves differ, which is of interest.
Well, I guess the direct acceleration takes place really in this diffusion region, which is microscopic. Microscopic means that its size is tied to the kinetic scales, but is independent of the system size.
Right,
If
so
you have a large system, you have many of these, but still, you have. If you have really a small system, then half of your domain is this diffusion region. If you have large system, then it's
smaller
a
fraction.
smaller fraction, right? So most of the particles would not go through this diffusion region, but would go through the separatrix and developing large plasmoids. Where other mechanisms.
But, yeah, okay, yeah.
That's the idea.
Right, so we can discuss more on this if you have questions at the end. So now to discuss their shares at final times, we find a reasonable convergence almost for weaker guide fields with domain size. As you can see, this purple line seems to roughly stabilize around 80%, let's say for the Fermi pickup combined share at final times, and for 0.3, maybe around 60%, and obviously these complementary quantities for direct acceleration, 20 and 40%. However, when we increase the guide field, it seems like we need larger domains to see the convergence through. As, for example, at 1.0, this trend seems to be continuing downwards. And so we would just need a larger domain to see this convergence. Okay, so we just discussed the shares of these different injection mechanisms, which are interesting, but their relevance is really understood when we contextualize them with respect to the downstream particle population. So the question really is, what fraction of downstream particles are injected? Because if we know that fraction, then we can look at these shares and multiply them by that fraction. So we know what fraction of the downstream is injected by this injection mechanism, right? And it's also interesting to know how this fraction varies with guide field and domain size. And so in other words, we're trying to find how efficient are these injection mechanisms. And so to do this, what we do is we begin with some downstream spectrum of particles, and we apply a fitting procedure to obtain the power law segment and the upper and lower limits on it. From here, we can define the injection efficiency, A to N, which is the ratio of the injected particle population over the downstream particle population, given by these intervals. So, in other words, just to show this visually, if we have a downstream spectrum, FDS, and we take this green region and divide it by the entire integral, we obtain this fraction of downstream particles that are injected. Okay, so what happens if we compare A to N to the injection shares, as we showed before, over this variation? What we find is that this initial spike from parallel electric fields corresponds to quite a large spike in A to N. It goes all the way maybe to a quarter of downstream particles are injected by this initial spike, which may lead some people to believe that this mechanism causes the ejection. But as we will see, especially for these weaker guide fields, that is not at all the dominant mechanism for injection. These two mechanisms actually play quite an important role by the time you get to the final times, even though there's a relatively smaller gain in A to N. Most of this is actually due to these other injection mechanisms.
And again, this is for a time slice. So how do you compute A to N?
A to N,
the time slice.
yes. So the spectrum itself evolves, and so that FDS I showed on the previous slide, this is also a function of time. So N is a function of time, NDS is a function of time, and A to N is a function of time.
But gamma injection is not.
But gamma injection is not a function of time. Yes, in principle, maybe someone could improve it to have gamma injection also function of time, but that's not what we've done in this study.
But N injection will include all of the particles that were injected throughout the history.
Yes.
So that's not a time slice, that's
Yes. So
cumulative.
yes. So A to N is a cumulative it shows a cumulative, whereas injection shear is defined instantaneously. So maybe this is kind of strange to compare it like this, but I'm just trying to illustrate that there's a connection here, which is not seen sort of, but these dominate, these Fermi pickup dominate later, but maybe it's not as dramatic in how A to N might change instantaneously.
And in any case, the rate of injection is somewhat order of magnitude constant over this time.
Well, it's not necessarily the rate of injection, it's the rate of injection over the rate of new downstream particles being introduced as well. So we also have to account for new downstream particles too. But yeah, this is correct, more or less. So if we increase the guide field strength even further, we find that the share by parallel electric fields improves quite a bit, as we saw before. However, the injection efficiency or number efficiency A to N declines. So that decline in Fermi pickup we saw earlier is even more dramatic due to there being fewer injected particles on the whole. In fact, while not shown, the total downstream particle population also declines with increasing guide field. And so the total number of particles injected by parallel electric fields actually declines a little bit by about 25%. And some interesting little fact here is that for a strong guide field of 1.0, that initial A to N spike is owed entirely to W parallel. So as we can see here, this red line remains at 100% for during this entire initial spike, but nevertheless, at final times, there's a 30% or so of injected particles are from Fermi pickup, which is quite remarkable, I think. Any questions? We're moving on to part 2 now. So
your
How many slides do we have?
your hour is basically gone. It might be good to
yes,
maybe give a summary.
sure.
Yeah, how many
When the
slides do
person
we
is
have?
already.
Well, I mean, part 2 is a little bit shorter, but maybe that would be like 30 minutes. So we have more questions, but yeah, so I can briefly summarize this. Oh yeah, maybe this will be of interest since we discussed this earlier. This is how gamma injection varies across this parameter scan. Right, so if we have similar domains, it changes a little bit. Especially for 1.0, but the main trend is with guide field strength. In fact, this ratio doubles nearly with increasing guide field strength by an order of magnitude, which actually has quite important implications for
It grows.
It grows. Yes.
Okay, but it triples if for a guide field of 1, it triples with box size, right? From 5 to 15.
Yes,
Yeah,
yes,
yeah,
but well,
But if you concentrate on large domains, right?
yeah, so it seems like there's okay, well, it's not entirely clear for the weak guide fields, but it approaches a convergence. It seems to approach some kind
Okay,
of
for domain sizes.
Right. Right. So this is the main comparison I'm making when I talk about this. Okay. Yeah, and then I talk about energy efficiency, which is a whole nother thing, which helps us contextualize the post-injection energy gains as opposed to the injection shares, let's say. So let's have an entire analogous. This part 2 is sort of entirely analogous to part 1, just for post-injection acceleration rather than injection number of injected particles. Okay, so let's just have a summary of what we found. W parallel is the first to inject particles, but for weak to moderate guide fields, Fermi pickup processes dominate injection in the long term over W parallel. However, a strong guide field does suppress both of these mechanisms, causing W parallel to dominate. And what we also find with the efficiency is that it's suppressed with increasing guide field, which sharpens the decline in Fermi pickup injection. For post-injection acceleration, we didn't get to go through it, but the story is similar. W perpendicular electric fields are suppressed, and the parallel index is steepened, and the injection energy increases, which also decreases the energy efficiency quite significantly. With domain size variation, what we find is that the initial current sheet length, Lx, the horizontal domain size, plays actually a pretty important role in controlling the saturation timescales of all the quantities we discussed in this seminar, as well as ones we haven't had time to discuss in the seminar. And so that's actually something quite interesting. And so one prospect is that if somehow these saturations can be inferred from signals, observational signals, that length Lx of the initial current sheet might be able to be inferred. And so on the topic of convergence with domain size, for some quantities we find convergence, for other quantities maybe we're coming close to convergence. It seems that using a system size of Lx greater than 500 or so, or in other words, 3,500 skin depths when using magnetization of 50 will be enough to capture most of the limiting behavior that we studied in this talk. And of course that depends on what quantities you want to look at, but just for the quantities we've looked at, this will suffice. And so I'd just like to have some acknowledgements. I'd like to thank my mentors, Dmitry Uzdensky and Fan Guo, who's on Zoom, for their continued advice and encouragement during my period of research. Thanks, everyone.
Okay, I'm gonna